Okay, in this video we're going to talk about operations with complex numbers. So in the last video we talked a lot about imaginary numbers and what an imaginary number was and where it shows up in our quadratic solutions. Well, today specifically we're just talking about operations with complex numbers. So remember that an imaginary number stems from finding a radical that has a negative inside of it when we have an even index, so a square root. Say the square root of -4, we talked about how the negative represents the square root of -1, and the square root of 4 is 2, so instead of writing 2 times the square root of -1, we represent -1 square root with an I, a little cursive I. With our number system, remember that any time we have a real number and an imaginary number, so if we have a real part, and we have an addition or a subtraction sign there, and we have an imaginary number part, this together creates some sort of complex number. Complex numbers are actually awesome. They only have the two parts. So either it's a real number, like 10, or it's an imaginary number, like 2i. So when we talk about operations, we're talking about adding, subtracting, multiplying, dividing them. And again, when we talk about like terms, adding or multiplying or any of that, there's really only two like terms. There's either the real part or the imaginary part, and we combine those. So let's look at kind of what happens when we add and subtract them. First of all, adding and subtracting complex numbers. Again, it's not important necessarily that you have all of this information written down. Those of you that are working in the old guided notes book, you'll have these pages within that. I believe it's found in section 4.1e if you want to find it as you go through this video. Otherwise, just take notes on the parts that you feel would help you the most. You're welcome to pause the video at any time. So first of all, adding and subtracting complex numbers. Adding and subtracting complex numbers means just combining the real parts, like terms, and the imaginary parts, like terms. So again, if I want to add, this example right here says simplify the expression 3 plus I, so there's a complex number, plus 4 minus 9i, a second complex number. All I do is add the like terms. Well, in this case, 3 and 4 are both the real parts, so we would add those to get 7. We would then combine the I and the -9i and get -8i. So when you add these two complex numbers, you end up with 7 minus 8i. And the cool thing about complex numbers is they always simplify down to another complex number. So no matter how many crazy terms you have as you perform the operation, they'll simplify all the way back down. So let's try a few just simple examples, and you'll see the I is just basically going to work like a variable. So on part A, if I was, again, make sure we know this is addition, so I'm just combining like terms. Looks like we have 4, we have a 10 here that are the real parts, so we add 4 plus 10 is 14. Then you have -7i plus 3i gives us a -4i. So we just combine those. On B, this one is subtraction, so just make sure you account for that negative there. So when you combine these, right, we've got 4, and then it's subtracting 3. So 4 minus 3 is 1. Then you have -7i, and again, you're subtracting 2i because of that subtraction. So -7 minus 2i would be -9i. Okay. So we're looking at that, adding and subtracting. And again, these can get long. They can have parentheses or not parentheses. But whatever we're looking at, we combine the imaginary parts and we combine the real parts. So on part C, 2i and 5i would combine to 7i. -7 plus 4 is -3. And we write them in what we call standard form for a complex number. Standard form is where we write the real part first plus the imaginary part second. And the reason we do that is when we graph them, they're going to act like a coordinate point. And if we're consistently writing them in that standard form, they will work like an ordered pair. Again, part D, these can get more complicated, I guess, if there's more pieces to it, but again, it works the same way. So we've got 3 plus I. I'm just going to pull things out of the parentheses. If we're subtracting, right, that's like subtracting a negative makes plus 10, and subtracting the 15i, those are both in parentheses, so the negative applies, and then you have that positive 9 on the end. I would just find all the real number pieces, so 3 plus 10 is 13, plus 9 is going to give us 22. And then I have the imaginary I minus 15i would be negative 14i. So adding and subtracting. Multiplying complex numbers. So when you're multiplying, you use distribution, right? Or FOIL or the box method. Anything that we've been applying when we multiplied radicals or other binomials. And again, they work just like the binomials. So you can kind of look at this example here. If we're multiplying the expression 4 minus 3i plus 5 plus 2i, we get 20. And then we continue to FOIL 4 times 2i, that would be 8i. Negative 3i times 5 is negative 15i. And the negative 3i times 2i is the negative 6i squared. Now you'll notice in this next step, they're just combining real parts and imaginary parts. But the interesting thing is they simplify this term right here, negative 6i squared, down to negative 6i times negative 1. And I'm going to show you why that is the case. If we know that I, by definition, is equal to the square root of negative 1, then we know when we see I squared written in an equation that if I were to take the square root of negative 1 and square it, squaring a square root is like canceling or undoing the squared. So anytime you see I squared in an equation, I squared is just equal to a negative 1. So we just replace it with negative 1 and simplify down once again. Okay? I squared is equal to negative 1. Really important in simplifying. So let's try this on these examples down here below. So part A says simplify the expression. So again, I have a binomial and a binomial, so I'm going to go ahead and FOIL this. 3 times 4 would be 12. 3 times negative 7i is negative 21i. I times 4 is positive 4i. And I times negative 7 is negative 7i squared. Again, if we're just combining like terms to simplify it down, these two in the middle, right, those have an I with them. This one on the end has an I squared. So as I simplify, the 12 is going to stay where it's at. I have negative 21i and a 4i. So that'll become negative 17i. And then remember, this is just negative 7 times, and I squared is equal to negative 1. So whenever we see an I squared, we just know that we multiply that value by negative 1. So this is really like 12 minus 17i plus 7. So we would combine the 12 and the 7 because 7 is now a real number part. And we would get 19 and then bring down the negative 17i. Notice once again it simplifies all the way down to a single complex number. Okay. On part B, again, if you just have two terms here we're multiplying, we do the 5 times negative 3 is negative 15. I times I, again, is I squared. Again, we know that I squared is just negative 1. So negative 15 times negative 1 is equal to positive 15. Again, no matter how many of these you do, it's really just it's just about simplifying the I squared in a correct manner. So let's do one more of these. If I'm distributing here, again, I get 12i. I multiply 3i times negative 7i, and I get negative 21i squared. Again, that I squared is equal to negative 1, so that thing really is just going to change the sign of that 21 when I simplify. So I could write it as 21, because we like to write the real part first in standard form, plus the 12i that was already there. Okay. That's multiplying. Let's talk a little bit about what happens when we multiply by what we call its conjugate. We used conjugates when we talked about rationalizing a radical denominator, so I just want to bring it back to something that we know. Remember when we had something like the square root of 3 over 2 plus the square root of 5? If we wanted to get rid of the radical in the bottom, we multiplied this binomial by what we called its conjugate. We said, well, if we take this same binomial but change the sign, so 2 minus the square root of 5, and then do the same thing to the top. We said when we do that, those middle terms cancel out and everything simplifies. I'm just going to finish this kind of to show you. On the top, that distributes in, right? And we get 2 square root of 3 minus square root of 15 all over. And on the bottom, we ended up with 2 times 2 is 4. Then we got a negative 2 square root 5, a positive 2 square root of 5, minus a square root of 25. And these two middle terms canceled nicely. And on the bottom, we just had that 4 in the front, minus the square root of 25, which is 5. And we were able to get rid of, I'm just going to rewrite the numerator, essentially the denominator's radicals. Same thing kind of applies when we take a complex number. Complex numbers always have a conjugate. So if 3 minus I is my complex number, its conjugate would be 3 plus I. So it's going to be the same binomial, but again with the opposite sign. And when you multiply a number by its complex conjugate, notice when we FOIL this out, we get 3 times 3 is 9. 3 times I is 3i. Negative 3i, when we multiply the negative I times 3, and negative I times I is negative I squared. So notice once again, just like with the radicals, those middle terms are going to add to 0, or we call that cancel out. And we end up with 9 plus 1, and we get a 10. Anytime you multiply a number by its conjugate, the imaginary piece goes away, and we're able to have our result be just a real number. So let's just try a couple of these. This says for each complex number, we're going to state the conjugate, then multiply the complex number by its complex conjugate. So if my number here on number 1 is 10 plus 3i, then the complex conjugate would look like 10 minus 3i. And if I wanted to multiply those two together, I would have 10 plus 3i times 10 minus 3i, and I would go ahead and distribute this. So we multiply here, we get 100. 10 times negative 3i is negative 30i. Again here we get positive 30i. And 3i times negative 3i is negative 9i squared. So as I simplify this, again, the negative 30i and positive 30i are going to add to 0 or cancel out. And then remember, I squared over here on the end is always equal to negative 1. So if I do negative 9 times negative 1, that gives me just a positive 9 there on the end. I still have this 100 up front, so total, when I add that together, it's going to be 109. Okay. Again, it always results in some sort of real number. The imaginary part will go away. So we use these conjugates to actually help us divide complex numbers, or in other words, rationalize denominators, just like we did with radical expressions. So I'm going to scroll down here and walk you through a couple of these examples, and then we'll do one together. Again, the goal with any complex number, so you can see a bunch of examples down here, is in simplified form, it should be in standard form. So there should be a real part, even if it's a fraction, plus or minus, whatever symbol we need to use there, the imaginary part. So notice these are just kind of one big fraction, and we want to be able to get the imaginary numbers out of the bottom and write them in standard form. So in order to do that, if the denominator is just one term, you really just need to multiply the top and bottom by I. And that allows the I to come out of the denominator. Just simplify as much as possible. Notice down here at this example, we've got 4 over 5i. If I go ahead and multiply the top and the bottom just by I, then I end up with on the top 4i squared over 5, just 4i over 5i squared. The I squared is equal to negative 1, so that denominator really just becomes negative 5. So here, with the 4i on top, we could write this as negative 4/5, right? And then I. So that simplifies it down to the complex standard form. There really is just no imaginary part here. So in this case, oh, I apologize again, there's no real part. A plus, and then you have the negative 4/5 I. The A is just equal to 0 in this case. If you have a binomial, so notice over here there's a binomial or two terms in the bottom. This is where the conjugate comes into play, because we know that if we multiply by the conjugate, the i's go away. So notice here the 2 plus 5i. What we chose to multiply by was 2 minus 5i, and anything you multiply on the bottom has to also multiply on the top. When you do that, you just go ahead and FOIL on the bottom, and you go ahead and distribute on the top like we did with radicals. Which will allow you to come up with something you can simplify. So let's go ahead and do this. You'll notice at the end they definitely have this in standard form with their real part written here and the imaginary part. So we're going to try one of each of these, and we'll finish off this video with dividing these imaginary numbers. So first of all, number 4, let's look at this one. 6 over 7i. Again, this is just a monomial, so really to get rid of the I just need to multiply the top and bottom by I. Now if I multiplied it by 7i or negative 7i, it wouldn't really matter. But notice on the top I now get 6i over 7i squared. Remember that I squared is equal to negative 1, so this is really just 7 times negative 1. So this is like 6i over negative 7. And we would just write that as negative 6/7 times I. Okay, so it simplifies. Let's look at number 6 on here. So again, number 6 now has a binomial in the bottom. We've got 10 in the numerator, 3 minus 7i on the bottom. So to get rid of a binomial, we want to multiply it by its conjugate. So remember, its conjugate is the same binomial but opposite sign. And anything we multiply on the bottom also has to multiply on the top. So let's go ahead and distribute on the top. We have 10 times 3, which is 30, and 10 times 7i, which is going to be 70i. Then on the bottom, we will go ahead and FOIL this. So 3 times 3 is 9. 3 times 7i is positive 21i. Distributing the negative 7i to the 3, we get negative 21i. And negative 7i times 7i is negative 49i squared. So on the top here we have 30 plus 70i over, it looks like these 21i and the negative 21i will go away there, add to 0, and we get 9, right, minus 49 times negative 1. So really that's just 9 plus 49. This is going to be 58. Now in writing our final answer, we are going to generally split that up. So this would be like 30 over 58 as our real part, plus 70 over 58i as the imaginary part. And then I believe those fractions will simplify. So we can go ahead and simplify each of the fractions to write it in its most simplified form. So if we cut each of those in half, we'd have 15 over 29 plus, and we'll kind of do the same thing with this other fraction and split those in half and get 35 over 29i. Okay, this is its simplest standard form. Your calculator will allow you to do some of these if you have the TI calculators. So I just want to make you aware that it will go through and do some of the multiplication and division to allow you to check your answer. But I would definitely practice these by hand. Just being able to simplify essentially the I squared and knowing how to use the conjugate to help simplify and write a division problem of